All right, welcome back. We're going to continue the 2.2 notes. Before I do that, I just got to toot my own horn. So in class on Thursday, right before the end, I shared my football predictions, and I discussed how the Kansas City Chiefs would beat the Houston Texans 34-21. Well, I was pretty close, 34-20. And in fact, it would have been 34-21 if Houston did not go for a 2-point conversion on one of their touchdowns. If they went for the extra point, I would have been exactly correct. So you could let me know later that you're really impressed with my prediction capabilities. So my prediction here for the 49ers Cardinals is 28-21. However, I don't know if that game's going to happen. The air quality is pretty horrible. It's like 250, even, excuse me, I'm coughing right now, right? 300. So the AQI is pretty high, so who knows if that game's going to happen, or if they move it to a different location or play it a different day. But that's my prediction, 28-21. We'll see if I'm lightning strikes twice for me. But yeah, I was pretty pleased with my prediction for the Thursday night game. It's always good right out of the gate to start strong with your predictions. Oh, that's basketball stuff. Okay, let's get back to math here. So let's keep applying our theorems as we've discussed. So what's going on with example 6? So we talked about earlier in the notes, and actually I probably should even open up the completed notes from prior. That sometimes might be a good idea, you know. Fill out notes. And by the way, fill out notes are in Schoology as well. If you feel like you didn't quite catch something, and maybe it's a little tough to kind of rewatch parts of the video, you do have that capability. So I do put them all in Schoology, all the completed notes for each unit. So we did talk about the limit as 1 over x, sorry, the limit as x approaches positive or negative of 1 over x equals 0. So going back to the 2.2 notes, in example 6, you would imagine that we probably expect the same thing for a and b. But if we just use our properties just to prove it, you know, we know that this just means the limit as x approaches positive or negative infinity of 1 over x times 1 over x times 1 over x. So each of these individual ones were 0, right? So essentially you're just doing 0 times 0 times 0, which of course is 0. Likewise over here. I mean, you're doing it 7 times, or you could think of it as the limit as x approaches positive or negative infinity of 1 over x raised to the 7th power. So you're raising 1 over x to 7, or the limit of 1 over x to no 0 raised to the 7th power is still 0. So those should be pretty straightforward. So what this tells us is that the limit of this general function 1 over x to the n is going to be 0, with the assumption that your n value, this exponent here, is positive. Otherwise, then you're going to get something kind of weird, right? Like this case, that's x cubed, which of course is a polynomial function. As x gets forever big, y gets forever big, or forever small. So you do got to be mindful about that. But you know, as long as your n's positive, we can make that assumption. Now, you do have to be mindful that sometimes if you do have a fraction exponent, like that's root x, we know this, right? Remember, we spent all that time doing this in the summer assignment. That does not exist because you can't square root negative numbers. But this one's going to be still 0. When you're doing 1 over root x, if you were to graph that, you're still going to get, you know, a graph that kind of looks like this. And it's going to be going towards 0 as x approaches positive infinity. So sometimes you have to be mindful when you're dealing with fraction exponents. If there's a even number in the denominator, that you're going to have a restricted domain. So be mindful about that. we'll keep moving. So let's look at more rational functions. And now this one, something is that you guys have talked about quite a bit in Algebra 2 and pre-calculus. You might remember, yeah, I'm getting a little ahead of myself here. That's okay. I was going to give you the generalization, but let's not do that first. So here we have A, B, and C. And notice how, well, actually, I'm going to somewhat do the generalization. So rational functions typically take on this form. And there's three cases to consider. If m is bigger than n, m equals n, and m is less than n. Usually some students will just memorize this and they'll remember what you get for your asymptotes. But let's actually take our calculus approach here. Let's look at this from a limit perspective. So you divide both numerator and denominator by the large power of x in the denominator. So what that means is that what if the largest power of x in the denominator, so that's x4, that's x5, and of course it's x3. So what if I divide this, so let me kind of write it over here, so I need a little space. What if I were to do this as an approach? 2x4 plus 7x cubed, I'm going to put that in parentheses, 3x4 plus 1, put that in parentheses, change color for a bit of contrast. What if I multiply this by 1 over x4? Or multiply this by 1 over x4? So what I'm doing is that for limits of rational functions as x approaches positive infinity, that's what I have. I do have a rational function, x is approaching positive infinity, divide both numerator and denominator by the largest power of x in the denominator. Well, this is my denominator, the large power of x is x4, and I'm dividing both numerator and denominator by x4. But multiply by 1 over x4 serves the same purpose, right? When you divide by x4, you can multiply by its reciprocal, same thing. Like if I divide by 2, I can multiply by 1/2, same thing. If I do that and clean it up a tad, here's what's going to happen. I'm going to get 2x4 over x4 plus 7x3 over x4 plus 3x4 over x4 plus 1 over x4. If you simplify, 2x4 over x4 is 2. That's 7 over x. That's 3. And that's 1 over x4. Now, if I use my limit properties, I could continue kind of breaking this down in a very detailed fashion if I so desire. But essentially, what I know is going to happen is that if I take the limit of this part, that's going to be 2 plus 0. If I take the limit of this part, that's going to be 3 plus 0. Actually, off to the side here, I will get a little detailed. If I just did this, as long as x approaches positive or negative infinity of 2 plus 7 over x, it's kind of like using my limit properties, right? Like, hey, the limit as x approaches positive or negative infinity of 2 plus the limit as x approaches positive or negative infinity of 7 times 1 over x. Well, I know that's just 2 for this constant here. That's going to be 7 times 0. So ultimately, I just get 2. And for the denominator, if I follow the same kind of logic, I'll get 3. So I know that my limit here is going to be 2/3 when that happens. And do note that the highest exponent in the numerator was the same as the highest exponent in the denominator. It's kind of like the m equals n case. And we also know that when you take the limit as x approaches positive and negative infinity of a function, that gives rise to a horizontal asymptote. So we're starting to see this graphical algebraic connection here now. That, oh, okay, by doing this limit as x approaches positive infinity and doing a little algebra, as I did here, as I did all over here, I got 2/3. That's also going to have a horizontal asymptote too. So I'm seeing a connection here. The horizontal asymptote here is going to be y equals 2/3. And so apparently when those are the same, I can just take the ratio of the leading coefficients. That's why that works now. That's why it works, because when we use some limit properties, that's what we, and then worked out through the algebra, we got that. And we also saw that in the earlier notes that as you go on left and right ends, Those are horizontal, that's a horizontal asymptote. If you do the same kind of process for B and C, I'll need to clear the screens and need some space. If you do the same kind of process here, you have 1 over x to the 5th and 1 over x to the 5th. So what's going to happen is that you have 2, so remember, you divide by the largest part in the denominator, so you have 2 over x plus 7 over x squared, 3 plus 1 over x to the 5th, the limit as x approaches positive or negative infinity. Well, if I work all that out, that's going to be 0 plus 0 over 3 plus 0, so you just get 0. Plus think numerically what's happening. The denominator has a much higher exponent. X gets really big. The denominator is going to increase ever more quickly than the top. So of course we numerically expect that to be y equals 0 for the limit. Graphically, if you do it, you're going to see the same thing if you were to put some decimals. And algebraically now, we're seeing that as well, using this technique of multiplying top and bottom by 1 over x5. So now we're seeing how all 3 of these things, the algebraic, the graphical, the numerical, they're all connected. And then for h, the highest exponent here is 1 over x cubed. To work all that out, I get the limit as x approaches positive infinity. Now it's going to be 2x plus 7 over x squared plus 3 plus 1 over x cubed. Now, if I evaluate that, you're going to have 2 times infinity essentially, plus 0 over 3 plus 0. So essentially, your limit won't quite exist. Or you could say it's plus or minus infinity, I guess, if you want to say that. But you're going to have an issue here because essentially, now you're taking the limit as x approaches positive infinity of 2x. Well, 2x is just a linear function. It looks like this. Of course, as I go forever to the right, y is going up forever. Of course, if I go forever to the left, y is going down forever. So that's why we don't have horizontal asymptotes for this. When the numerator has a higher exponent than the denominator, or when the numerator has a higher degree. Where here, the horizontal asymptote for b was y equals 0. So hopefully this kind of gives you a better understanding of how horizontal asymptotes behave for rational functions. A lot of times students just memorize, like, okay, if m equals n, I get this, m's less than n, I get this. But if you take it from a limit perspective and think about it graphically, think about it numerically. Numerically, the way you think about it is just plug in large numbers. And naturally, the higher exponent increases more quickly. Graphically, you can just see what's happening. And of course, algebraically, I'm giving a technique here. Multiply by 1 over x to some power. That power depends on what is the highest exponent in the denominator. And going through some of the algebra and using some of our limit properties, we can confirm algebraically what we saw numerically and graphically. And that gives rise to the horizontal asymptotes. So this is a very important discussion here, and we're going to explore this more, obviously, when we meet in person. So looking at all these, our horizontal asymptotes again, for f of x is y equals 2/3, y equals 0, and we didn't have one for the last example. So you can see down below, this is the general way of writing a rational function, where a rational function is a ratio of 2 polynomials, right? And m is the highest exponent of the numerator, n is the highest exponent of the denominator. If m is less than n, we get that. m equals n, we get that. The ratio of the leading coefficients. And of course, you don't have one. Instead, you have a slant asymptote, which you might remember doing in pre-calculus, but we're not going to talk about that right now. And I'm not sure if we even really do care for that in this class. And yeah, I mean, this is kind of what we call the eyeball method. So like on a multiple choice test, like on the AP exam, if they have, they ask you, yeah, then you could totally just rely on that and that's fine. Or if you're doing like a SAT or ACT exam, that's fine. But when I ask you to do it analytically, obviously our test will be free response, I need to see the work that we did on the previous page. The whole 1 over x thing, multiplying top and bottom and cleaning it up. I need to see that analytical work. You will not get full credit if you don't do the analytical work. So very, very important that you understand. And we're going to practice. Maybe we'll do, maybe when we start class on Tuesday, maybe we'll just start doing some practice problems like that, just making sure that you guys are getting it before we move forward with the rest of the 2.2 notes. Because I'm going to pick things up from the beginning of page 5. So again, hopefully you're watching this this weekend or on Monday, the day we have designated for asynchronous learning days, because I want to make sure we keep things moving here, right? So we're getting close to the end of page 4, which is good. The cat's got really quiet too, but I think my son's up, so I'm gonna have to feed him breakfast. Everyone's got to eat, right? Plus I got to do my NFL research for tomorrow too. So, which so far has been good, right? I was really close to that prediction. Anyway, so y equals b to the x. Here we have an exponential function. Remember, exponential functions could be growth or decay. In this case, we have growth, b is bigger than 1. For example, like y equals, you know, whoop, looks like my stylus died on me, which is actually fine because I'm almost done with this video anyway. I do have to do a video for my other stats class, but that's okay. I can use my mouse. So like y equals 2 to the x is one example, or y equals 3 to the x, and so forth. Of course, there's a point at 1 comma b, b being the base of your power. And there's a point at 0 comma 1, the initial value, x equals 0. And the 0 power is always 1. One that we tend to use often is y equals e to the x. And we just want to investigate those limits. So we do recognize that these have horizontal asymptotes, right? And that's probably when you first learn about horizontal asymptotes, when we talk about exponential functions. And that's why sometimes people misconstrue this as a boundary. In this case, yes, it does act as a boundary. It's a floor for this graph. Like, you know, it can't go below 0, obviously, because 2 to the x cannot equal 0, right? How do you raise 2 to some power and make it 0? 2 to the x also is not less than 0, right? How can you make that negative? So, you know, we know that this has to be positive, right? You know, that's what we talk about range and domain, right? Domain here is all real, but the range was y is greater than 0. Or in interval notation, your domain would be negative infinity to infinity, but your range would be from 0 to infinity, 0 not included. So just by looking at the graphs, we realize that if I take the limit of e to the x, or anything, you know, where the base is bigger than 1, because e is roughly 2.7, and x is approaching negative infinity, the limit will be 0. Now, if I do a decay function, like in this case, this is decay, you know, if I do like 1 over e to the x, or 1 over 2 to the x, or just e to the negative x, so keep e like as it is, but when you make it that, that's 1 over e to the x. But now x is approaching positive, so you're going to the right, y is getting closer and closer to 0. So you could actually work out something a little more complex here by just using these properties. So for example, limit as x approaches positive infinity of 7 minus 5x squared. Well, if x approaches infinity of a constant, it's still going to be 7. And if 5 over x squared, now we know that's just going to be 0, because, you know, 1 over x squared is 0 times 5, whoop-de-doo, still 0. E to negative x, I know is going to be 0. And plus 3 is 3. So I'm actually evaluating this limit for each of these 4 things. And use my limit properties, 7 minus 0 times 0 plus 3, I just get 21 straight up. So that's how that limit's found. And we'll try maybe one more example before I end the video. And then we'll pick things up from the top of page 5. So warning, Workable as x approaches infinity presents a special challenge when we can't use substitution. We can't do regular arithmetic with infinity and undefined quantities. So remember, 0 times 0 is 0. We know this. 0 times any constant is also 0. But 0 times infinity, that's kind of weird, right? I mean, is it 0? Is it infinity? Is it a constant? It really depends on the situation you have. So we have to be a little mindful about that sometimes. But I mean, this was easy. I mean, yeah, we had 7 minus 0 times 0 plus 3. And that was easy, right? That was 21. But let's look at example 9 here. You can break this up. 7x over x minus 10 sine x over x. And this is the limit as x approaches negative infinity. Yeah, I'm looking at example 10. I'm glad I'm going to save that for Tuesday. I don't want to do that right now. So this is going to be our last example here. And of course, 7x over x is 7. That's 10 times sine x over x. Now, sine x over x, that limit's going to be 0 as x approaches infinity, or negative infinity. And for the constant, it's just 7. So the answer is just 7 minus 10 times 0, or straight up just 7. That's what we see there. So yeah, we're doing a constant times 0. We're okay. Not a big deal. But we do have to be mindful that things can get a little bit messy when you're trying to do 0 times infinity or something like that. We're going to talk about that on Tuesday. So anyway, I think that will end the video. There'll be a Google form questions. Please answer that. I'll probably put about 5 questions or so, just checking to make sure you understood what was discussed in this video. And then we'll just meet again on Tuesday. And again, football predictions: Niners 28, Arizona 21, if the game plays. Haven't really thought much about the other game, so I'm just going to be randomly guessing because I like to be accurate. So anyway, see you guys later. Have a good weekend.